A component would be any identifiable molecule, salt, sodium chloride, methane, carbon dioxide, water, any mineral, anything, any of that could be a component, right? And so what we want to do is do a material balance on this component, J. So right now, well, we'll say consider single phase flow, but actually we'll look at multi-phase flow and then go back to single phase flow at the end. And what you have is that you've got some amount of mass of this component, maybe it's sodium chloride, in your water, in your brine solution that's flowing, and it's going in through this one-dimensional reservoir. We could do the balance in 3 dimensions. That would just make the math a little bit more difficult. We're going to do the mass balance over this little gray box. We call it a control volume. It's got a length of delta X and an area A. And what we're trying to do is model the couple flow. So that's like velocity and flow of the brine solution, or if you have multiple phases. And then we want to do transport of that component. And we know that the transport can occur both by advection, where the fluid carries it, and by diffusion or dispersion, which is due to mixing. If we write that mass balance, we always write balances, whether it be a mass balance, an energy balance, a momentum balance, the same way. Whatever goes into my black box, my control volume, minus whatever goes out, is what's accumulated. So what we have here is mass N of J. So remember, N is a flux. It's a mass per unit area per time. So we multiply by area and time. This is what goes in, and this is the J, the component that goes out. You could have some generation due to wells, right? You could be injecting or producing that component, or you could have a reaction that creates or makes that component go away. And then you've got an accumulation term here. So this is the mass at time t, and this is the mass at time t plus delta t. You might have more or less J in the future than you do now. Okay, so now we got this equation, and we'll define Wj in a moment, but remember it's a concentration, it's a mass per unit volume, and again N was a flux. So if I divide through that by the area times delta X times delta T, and of course area times delta X is delta V, the volume, then you get this equation. Now the units have changed now. Now they're mass per unit volume per time, each of the terms, but it's still equivalent because I divided everything by the same. Then I can make that control volume, that delta X, I can make the time that I do the balance, delta T, as small or as big as I want. I could do a nanosecond or a million years. I could do a nanometer, or I could do kilometers, right? What I'm going to do is I'm going to make it small. In fact, so small it'll be infinitesimally small. So I'm going to take the limit as delta X and delta T go to 0. And we know from our calculus class that when we got a denominator like this and we take the limit as delta X goes to 0 or delta T goes to 0, you get a derivative. In this case, it's going to be a partial derivative. So what we have here is you take the limit as delta X goes to 0, you get the partial of your flux with respect to X, and you get a partial of Wj with respect to time. Why are they partial derivatives? Well, because these things depend both on space and time. So they depend on more than one variable, both X and T, so you'll have to take a partial derivative there. So when you do that, you get a solution, you get substitution into your component balance, we get this partial differential equation. So the partial of concentration Wj with respect to T minus the partial of your flux of component J with respect to X, and then you have your source term is going to be equal to 0. All right? And then, so what is the concentration? Wj. Wj is the amount, the mass of J per unit volume in your, in the reservoir. And Wj, so it's a mass per unit volume. Keep in mind that the component J could be in any phase. It could be in the aqueous phase, the oleic phase, the gaseous phase, or it could be in all of the phases. it can also be adsorbed onto the rock surface. Now, last time I had talked about adsorption, and I made a distinction between adsorption versus absorption. Adsorption would be when something stays on the outer surface. So it's like creates a film on the outer surface. And so if you had, I don't know, maybe an example would be if you ever gone into like a, kind of gone swimming in some natural springs or something where they had some rocks in the water, and you stood on the rocks and you can kind of feel that grimy, stuff on the surface of the rock, right? That was, some sort of fungus or something that probably adsorbed onto the rock surface. That's adsorption. Absorption is if it goes inside the medium. And so the example I would give is some sort of sponge. So if you take a sponge and soak up, water or something, then it's going to go inside there. And that's absorption with a B. Okay? So, we've got this concentration. And WJ says that, well, we can have some sort of concentration, CJW, that's the mass per unit volume, pore volume of, that's a mass per unit pore volume of component J, in a phase, and so you multiply that by the saturation of that phase. So you've got, J in the water times the saturation of the water, J in the oil times the saturation of oil, J in the gaseous phase times the saturation of the gaseous phase. This is porosity. And then you could have concentration adsorbed onto the surface. We don't generally have absorption, right? These are rocks. It's not easy to soak it up like a sponge, but you do have adsorption. And this is 1 minus the porosity. Or you could put this whole term in parentheses as just one term, which is the concentration of component J. Then you have the flux. And we talked about fluxes and different mechanisms. And we said that one mechanism for flux, for component transport, is advection. Is that the flowing fluid literally carries the component with it. Right? And so I said last time that if the fluid is flowing 1 foot per day and we only had advection, and I injected a bunch of particles, right, like I dumped a bunch of salt or something into the water, then after 1 day, all of it would move exactly 1 foot. Right? It's carrying it with it. However, we also have this mixing phenomenon. Okay? You have diffusion. Okay, we know about diffusion, right? We said that an analogy would be is if you're cooking in the kitchen and it creates the smell. As time goes on, you can start smelling at further parts of the house because concentration goes from it, because it transports from high concentration to low concentration. But dispersion is much bigger, and it has to do with mixing that occurs. And because of mixing, if I dump all that salt in at time 0 and I wait 1 day, well, on average, it'll go 1 foot, but some of the salt will go further and some of the salt will go less far. And so you've got some mixing that goes there, some spreading phenomena. And so that's what this dispersive flux is. So if I put all that together, if I put in my definition of NJ and I put in my definition of WJ, my component balance for multiple phases, by multiple phases I mean aqueous phase, oleic phase, and gaseous phase, looks like this. Okay, it's kind of complicated. We can simplify that for the case that, first off, let's say that there is no adsorption. We'll come back to that. I think we're going to talk about adsorption more next week. But for now, let's just assume that there's no component that adsorbs onto the rock. And then the other assumption I'll make is let's just talk about single phase flow right now. So rather than having an aqueous phase, an oleic phase, and a gaseous phase, let's just have one of those phases, an aqueous phase. For example, I mean, it could be an oleic phase as well, but maybe we're talking about an aqueous phase and we're injecting some salt or some tracer in there. Well, then the partial differential equation reduces to this. This is my accumulation term, C sub j is the concentration component j in the volume, pore volume. U is the velocity, so it's how fast fluid is flowing. So this is the advection term. This is accumulation. And this is my dispersive term. And then I could have some sort of generation from wells or reaction. If you solve this partial differential equation, you'll get the concentration of component J at every location X and every time T. Okay, now this is a complicated PDE. As it's written, you can't solve it analytically. You'd have to use approximate numerical techniques that you'll learn in Dr. Foster's reservoir simulation class if you take it. To complicate things further, this velocity U might change with space and time, right? The velocity might be a lot larger near wells and in fractures than in other parts of the reservoir. And to determine the velocity, you need to solve the diffusivity equation. This probably looks familiar to you from Reservoir 1, and we talked about it at the beginning of the semester. Once you get the pressure field, you can take the derivative and use Darcy's law, and you get the velocity everywhere. Okay. Now, all that's kind of complicated, and I think beyond the scope of what we want to talk about in this class. The point being is that we've got this PDE that we want to solve for concentration. But let's simplify things a little bit. Okay, we're already only talking about one dimension, so we've already simplified it a little bit already. Okay, of course we simplified it by doing single phase flow and no adsorption. But let's also say that the velocity is constant. And this is common in our experiments in the laboratory. We'll get a one-dimensional like rock core, and we'll flow through that. I'm going to go get a little prop here. So let's pretend that this is a 1D cylindrical rock, this roll of paper towels here. Okay, and it's about a foot long, so it's actually quite perfect. And what we do is we might inject fluid on one end at a constant velocity, and it comes out at the other end at a constant velocity. We do these experiments all the time. We do them here at UT, we do them in our labs, and you go to any of these major oil companies, they have laboratories that do those types of things. And they do that so they can estimate properties, so they can make predictions in the field. Well, if you have a constant velocity U, and we could also assume things like constant porosity phi, then it really greatly simplifies the PDE. Okay? Basically what it means is that anything in those derivatives, the porosity I could pull out, the velocity I could pull out, and the dispersion coefficient is a function of velocity, or the Peclet number. We talked about that earlier. And if velocity is constant, then the dispersion coefficient is constant, so I can pull it out. And just to make it look easier, I've dropped the subscript J. So we're talking about this is the concentration of some component. Okay, and I'm saying we only have one component right now, so we'll call that just C. And so this is the equation that we have. Now, it doesn't look particularly simple, but it doesn't look all that bad either. Okay? It's not all that much more ugly than maybe a differential equation you saw in your differential equations class. Although most of the differential equations were probably ordinary differential equations. One thing we often do is we like to non-dimensionalize it. So we're going to define the non-dimensional concentration so that it's bound between 0 and 1 in this way, where C and it is the initial concentration and I and J is the injected concentration. XD is the dimensionless length, so it goes from 0 to 1. TD is the pore volumes injected. We've seen that before. So it's the volume injected divided by the pore volume. And then we have Peclet number, and Peclet number is the ratio of advection to dispersion. Okay, so advection is clearly in the numerator. You've got the velocity, and dispersion is the denominator, so you get D. So if you're flowing very fast, and very fast is all relative, even 1 foot per day is pretty fast in reservoirs, then your Peclet number is large, and then advection dominates over dispersion. And in fact, you might be able to ignore this dispersive term altogether, which simplifies things. And if the velocity is low, though, then your Peclet number is low, in which case this last term is pretty important. In dimensionless form, you can write the equation like that. And we like having dimensionless equations because then we just kind of get a universal curve that we could use regardless of what the dimensional variables are. And then we had some initial conditions, which if C is equal to C initially, then CD is equal to 0. Then we can inject this component 2 different ways. One of them is that all of a sudden at some time, and we'll arbitrarily define that as time 0, we start injecting continuously. So let's say I had fresh water in my one-dimensional reservoir, and then I just started injecting salt water. I inject that salt water continuously for a very long time or forever. In that case, at all times, the dimensionless concentration is 1. That's what I'm using here. Later, we'll do something a little bit different, where I just kind of do it's like a dump salt in all at once, or over a short period of time. And but then I go back to injecting fresh water. That'll be a little bit different solution. I'll revisit that in a moment. And then there's another boundary condition that if you go to very, very large x, that it's equal to 0. Now that's a weird boundary condition because the length of our reservoir isn't infinite long, but that's okay. Mathematically, that's how we treat it, and it's very, very similar to what we learned in Reservoir 1 and what we learned about infinite acting aquifers. Is that if you go out far enough to very far distances, then the concentration, or previously the pressure, but here the concentration, is equal to whatever it was initially. So CD is equal to 0. So let me come back to here and talk about what the solution looks like. And we started doing this just a little bit at the end. So if you plotted the dimensionless concentration versus the dimensionless distance xd, it's always going to be bound between 0 and 1. And if the Peclet number was very, very large, like infinity, you would actually get something that looked like this. This is n Peclet number is equal to infinity. So advection very much dominates over dispersion. What does this say? This is at a particular time, TD. So this is at TD. You could do different times, and at a later times this front would move forward. Earlier times it would be earlier. But what this says is that if you had only advection and no mixing, no dispersion, then the concentration would be your injected concentration, 1, up until this point xd, and then after that it would just be whatever it is before. So in this case it is that literally that moving wall that I've talked about. Okay, we had one in multi-phase flow Buckley-Leverett theory, although it didn't quite look like this. You had a little bit of decrease, and that was due to the nonlinear fractional flow equation. But here, when you have advection only, it looks like this. Now I could also plot the concentration at the exit. I'll call it CDE. That's the concentration at x is equal to L, or xd is equal to 1, versus dimensionless time, TD. And if you had Peclet number is equal to infinity, what happens is that nothing comes out, none of your solute, none of your component comes out until TD is equal to 1. And then at TD is equal to 1, it goes up and you get concentration of 1. Remember, because you've got this moving wall, right? And it's going in and nothing's coming out, and then it reaches the exit, and then it goes up to that value. Okay, so very simple. Okay, reality is that we never truly have a Peclet number of infinity. And if you have mixing, if your Peclet number is less than infinity, if it's finite, then you'll have some amount of mixing. Okay, and so what that means is that it'll actually look more like this. Okay, it spreads out. Okay, and at the exit, what you have is you have a breakthrough time, kind of like we did in multi-phase flow. And that, it doesn't all come out at once. It kind of slowly comes out. Now, how much of mixing is depending on what the Peclet number is. So if your Peclet number was really big, like 10,000, then maybe this looks like this. Okay, but if it's smaller, then it looks more like that one I just drew a second ago. Same thing over here. So if your Peclet number is really big, maybe it looks more closer to that very discrete curve, but the smaller your Peclet number, the more smearing you have, the earlier breakthrough you have. So think about it. If you're flowing along over here, and I inject my salt, and it's flowing at 1 foot per day, and let's say that this is 1 foot, that's about 1 foot, then it'll take 1 day for the salt to come out if I'm advection dominated. But if I got a lot of mixing going on, then what happens is that some salt comes out earlier, so before 1 day, or before dimensionless time is equal to 1. But then even when it comes out, just a little bit comes out, then as time goes on, more and more will come out, and then there'll be a lag. So you go on for 2 days or 3 days or 10 days, and that concentration will be changing a little bit. Okay? It won't get to your injected concentration for some time. Make sense? Okay, so that's qualitatively what the solution looks like. I wanted to show you that before I showed you the mathematical solution. We could plot the mathematical solution to get those. So the mathematical solution is the dimensionless concentration CD, which is a function of both distance, xd, and time, td, is, I'm going to say approximately equal to, I'll explain why in a second, 1/2 times the, now stay with me, the complementary error function times xd minus td, 2 times the square root of td over Peclet number. Okay, and I say approximately, there is an extra term, but unless the Peclet number is very, very small, applications we don't usually deal with, that term is negligible. So for our purposes, this is good enough. Okay, so what does this say? Well, concentration is a function of distance and time. So if you know your position, that could be anywhere in my 1D reservoir, or it could be at the exit, which means xd is equal to 1. And it could be any time td, and you know your Peclet number, which is in there. Okay. Now, the function here includes this thing called ERFC, the complementary error function. You guys ever heard of the error function? You used it in another class ever? No? Okay. So it doesn't surprise me. But it is something that comes up a lot. It's very, very analogous to the exponential integral solution you learned in Reservoir 1. Remember EI, right? And it was this weird function, and it was really this ugly integral that was harder and impossible to solve. This is exactly the same thing. The complementary error function, first off, is 1 minus what's called the error function, ERF. Okay, so error function of some variable x is equal to 1 minus ERF x. So what is ERF? So ERF, the error function, is 2 divided by the square root of pi, 0 to some x of e to the minus x squared dx. Okay. Well, it doesn't look too bad, but the reality is that you cannot solve that integral analytically. You can't. So if your calculus teacher were to give you this and say solve it, then if you got an answer, it'd be the wrong one because you can't do it. You can't use integration by parts. You can't use any of the tricks that you learned in there. The only way you could solve it is numerically, and I'm sure that in 310, I don't know if you took Dr. Panatovich or Dr. Foster, but you learned things like the trapezoidal rule, right? Does that sound familiar? Numerical integration techniques. It's the area under this curve. So you'd have to plot e to the minus x squared and take the area between these two things. Fortunately for us, somebody else has done all the work for us. And if you were to go into Excel or Python or just Google it right now if you want. So put in ERF of open parentheses 0 or 0.5. It'll give you an answer, I bet, in Google, right? It's a function just like sine or cosine or any other function you've ever learned, right? It's just not one that we're all that familiar with. And you can put it into your calculator, or most calculators, Excel, Python, there's built-in functions for that. But I'll show you what the plot looks like. So if you were to plot the error function of some variable x versus x, this is ERF. This would be very small, like negative infinity, and over here you go to infinity, and this would be like 0. And then right here, the y-axis, this is -1. Positive axis is 1. In between is 0. Okay, then what you would get is this sine shape right there. And I should move this over here. Let's see. Yeah. So when x is 0, the error function is 0. Okay, if you want to check that, go into Google and put ERF, open parentheses, 0, close 0, and I bet that something will come up and says 0. Or you could do that on Excel or something. But this is the error function, and then remember, the complementary error function is just 1 minus that. So if the error function was -1, 1 minus -1 is 2, right? So that's that solution. And basically when we plot this, if we were to plot this in Excel or Python or something, then we would get these plots. Okay? We get those plots, and it seems hard, but again, Python and Excel have these functions, so you just plug in the equation and plot it, and it'll give you that. And it's clearly a function of the Peclet number. Peclet number is really, really big. Then you get this kind of straight front. Peclet number is smaller, you start getting this mixing and this spreading of the curve. Any questions about that? Okay. So again, we got our 1D reservoir. A lot of these concepts apply in 2 dimensions and 3 dimensions, but mathematically they're simpler in 1 dimension. So maybe we're injecting concentration of 1, and then we want to know what CD exit is, right? So that's at XD is equal to 1. And so what is CD at exit? Okay. Well, I can just plug that into the formula. I can put in XD is equal to 1. So if I did that, I would say CD at XD is equal to 1, and at all times TD, I get 1/2 1 minus the error function of, now it was supposed to be XD, but XD is 1, so it's 1 minus TD divided by 2 times the square root of TD divided by n Peclet number. Right? All I did is I used the equation, but I put in 1 for XD. Okay. That doesn't, so what do I do with that? Okay, well, I could just plot that, right? And that's effectively what I did here. That's what this plot is. I picked the exit, XD is equal to 1, and I plotted that last equation versus TD, and depending on what the Peclet number, that's what my curves look like. One thing that we do in the laboratory especially, actually we do this in the field too, we do a tracer test all the time, but we do it in both places, is that we do this experiment, and even in the field I would call it an experiment in the field, where we input this tracer and then we look to see what it is at the exit, or in the field it's at the producer well. And we track our concentration versus time, and we make a plot like this. Make a plot like over here. So this is the concentration at the exit, or concentration at the producer well versus time. And what we want to know is what the dispersion coefficient is, because that's not something that we really have a good handle on. Okay, we know what our velocity is. Okay, that we can kind of control. The dispersion coefficient is not particularly known. It's not something that you can measure very well in the laboratory. So we might want to know that. And by the way, this dispersion coefficient also gives us an indication of how much heterogeneity there is in the reservoir. And heterogeneity adds to mixing, and heterogeneity really hurts productivity in reservoirs. So you'd want to know that. So one thing you could do is you could just fit your equation to the data, and you could adjust it. Maybe you can do some nonlinear regression. So what we want to do is, so the goal is to use experimental data to estimate DL. That's the dispersion coefficient. One way to do that is nonlinear regression to get the Peclet number. And once you get the Peclet number is related to the dispersion coefficient, so you get that. Now, my favorite way to do nonlinear regression is to use Excel and to use the solver. So you minimize the sum of the errors between the data and the model. An easier way to do this is linear regression. As engineers, we always love making straight lines if we can. Straight lines are so much better than non-straight lines. And if we do straight lines, then you can do slopes and intercepts and things like that. So we're going to do a little bit of a mathematical trick here. We're going to take this equation here, and I'm going to rearrange it. So I'm going to multiply both sides by 2, then I'm going to move this over here, and so I'll get 1 minus that and move that over to the other side. So what you get is 1 minus 2 CD, I'll call it CD exit, right? This is CD at XCD is equal to 1, is equal to the error function of 1 minus TD divided by 2 square root of TD and Peclet number. Everybody see how I did that? I just did a little bit of algebra, moved some things around. So multiply both sides by 2, and then move the 2 CD over to the right, move the error function over to the left, and then equated them, so you get that. So we got this error function. If we take the inverse function of something, then it's like the opposite of it, right? So if you have like the sine of x and you take the arc, the inverse sine, then then it gets rid of that. So we can take the inverse function. And what I get is so you take the inverse function of both sides, the left side and the right side. And so then the inverse function of 1 minus 2 CDE is equal to, well, this goes away, and I can flip up the Peckley number onto the numerator.
Dr. Balhoff, can you move the page up, please?
Yeah, sorry about that.
Thank you.
Okay, so what I did is I took the inverse function on the left and right-hand side, and this is what I get. So the inverse error function of the error function is just gets rid of the function altogether. I'm just left with the argument. The Peckley number was in the denominator, at the bottom of the denominator. What I did is I flipped it up. I used a reciprocal, so it shows up right there. And yeah, okay, so now we got this inverse error function, and don't worry about it either, because again, Excel and Python and maybe even some calculators will do that for you. So you can take the inverse error function of some value. So what does this mean? So if I wanted to plot some data and get a straight line where the slope was the Peckley number, what would I put on my y-axis and what would I put on my x-axis? So what we want is something like y is equal to mx.
Mm-hmm.
All right. What if I made this y? What if I made this x?
Oh yeah, I was thinking you were wanting me to like rearrange it all. That's what I was thinking you were wanting me to.
Yeah.
Sorry.
Yeah, so we rearranged it to get to this place so that we could do this. So what this means, if I make a plot, so what I'm going to get is I'm going to get data of TD versus CDE. And that alone is not good enough. I got to put it into this form. So maybe I call this x and maybe I call this y. And if I plot y, or inverse error of 1 minus 2 CDE, and on the x-axis I plot 1 minus TD over 2 square root of TD, and I plot my data, there'll be some scatter.
Would you mind?
Yeah.
Thank you.
There'll be some scatter. Right? There always is anytime we do experimental data or field data. You draw a line through the origin, and the slope will be the Peckley number. Okay. So that's what I do, is that I go into the lab or I go into the field, and I measure the concentration at the exit of the producer well at different times. I can plot it as like that. I can plot concentration versus time. But if I rearrange the data, if I calculate this and I calculate this and plot those two things, I'll get a straight line where the slope is the Peckley number. And then I know that the dispersion coefficient is the velocity times the length divided by the Peckley number times the porosity. So I'll know how fast I was injecting. Maybe it was 1 foot per day or something. L is the length. P is and I'll know that. P is the porosity. I may or may not know that, but I'm going to show you well, maybe not today. Maybe I'll show you on Monday how you calculate the porosity, and then we just calculate the Peckley number from the slope. So this gives us the dispersion coefficient, and that's what we were looking for.
I had a question real
Yeah.
quick. Is the slope supposed to be that square root of NP?
Yeah, sorry. You're right. So it's the square root of the Peckley number. Very good. Thank you all, and have a good rest of the day.